Hello, everyone, and thank you for joining this talk by myself, Adib Mehrabi, and Dayn Wilberding. I work in the Advanced Technology Group at Sonos, where we conduct research into advanced rendering and immersive audio technologies. And Dayn is from the Design Group at Sonos, where he is focused on experience exploration. Our talk's entitled When Signal Processing Meets User Experience, How to Turn a Customer into an Audio Systems Engineer in 60 Seconds. So in this presentation, we're going to discuss the development and design of a feature called Trueplay, which exists on all Sonos products today. Trueplay is a user-facing software feature, which is used to adapt the sound of our speakers to the listening environment. And it was initially kind of developed and released 7 years ago, there or thereabouts. And a lot of the content we'll be presenting in this talk is from the initial development stages back in 2015. However, we hope that some of the learnings and the resultant approaches that came out of this work will be both interesting and relevant to the audience here today. So here's a brief overview of the talk. We're going to start with an introduction to Trueplay as a software feature and how we come to have such a feature, and then dive into the design and the development process for our most widely used version of Trueplay. But first, just want to take a moment to highlight that there have been many people involved in the work presented here today. Just some of whom are included in this slide. And there may be a few familiar faces in here to this audience from the audio signal processing and psychoacoustics community, and perhaps some less familiar faces. And one thing that this really highlights, though, is that although Trueplay fundamentally relies on audio signal processing, the success of the technology is in large part due to the multidisciplinarity of the team that's worked on it over the years. So what is Trueplay? Trueplay covers a range of technologies that perform in-room speaker correction for our systems in response to the acoustic environment, the speaker placement, and the listening area. And the ultimate goal of Trueplay is to bring our speakers closer to how they've been designed to sound by the audio systems engineers, the speaker designers, in any environment and placement. So there are actually three main versions of Trueplay today. The first version, which is also the main subject of this talk, is what we call manual Trueplay internally. And this was released in 2015 and was the brainchild of Tim Sheen, who was an audio systems veteran at Sonos, who actually only recently retired this year. And the main problem that this is solving for is bad speaker placement or bad room acoustics. And it does this by taking a system measurement and applying a spectral correction to the loudspeaker DSP. At a high level, the system plays a calibration tone, and then a measurement is done by the user by moving around the listening area with an iOS device. This measurement device then calculates a spectral correction, which is actually a set of bipod filters that get applied to the speaker. Now, the next version of Trueplay was released a couple of years later in 2017, and this was developed to address the problem of poor spatial rendering that's caused by poor placement of a soundbar, or again, poor room acoustics. Now, soundbars use loudspeaker beamforming to create a greater sense of immersion, and this relies on utilizing first-order reflection points to create kind of virtual loudspeakers, where discrete left or right or surround speakers would usually be placed. One of the major issues with reflection-based loudspeaker virtualization is that the reflection path for anything other than the center channel, the direct channel, i.e. the non-reflection channel, introduces significant delay compared to the center channel, as it has to follow the full reflection path. And this will be dependent on where the reflection points are, and we don't know where the reflection points will be in the end user environment. So home theater Trueplay essentially extends manual Trueplay spectral tuning with a spatial component. And this is illustrated in this slide here. So this requires the user to sit in their preferred listening area. The system plays stimulus tones that are again measured on the iOS device in order to measure the time of arrival and gain differences for each channel and apply corrections accordingly. Finally, the most recent version of Trueplay on some of our products today is automatic Trueplay. Whilst manual and home theater Trueplay work well for a variety of speakers that are generally positioned, tuned, and then left alone, aren't moved, they would not work very well for speakers that are being constantly moved around, such as portable devices, such as this battery-powered device that's shown in the slide here. So this would require the user to retune the system every time the speaker is moved, which isn't very practical. And for this reason, on our portable products, we've got a version of Trueplay which automatically retunes periodically or when the speaker is moved. And this uses the onboard microphones to measure what we call the self-transfer function. That is the transfer function between the drivers on the device and one or more microphones. And then this self-transfer function is then used to predict the in-room speaker frequency response using a data-driven model. And as I previously mentioned, we're going to focus on manual Trueplay for this talk, as it really is the foundation of all versions of Trueplay. And it also presented the most interesting challenges from a UX perspective, and it fits well with the theme of this year's conference, which is on human-centric design. But first, just to motivate the topic, why do we need in-room speaker correction at all? Well, it's fair to say that it was originally designed for music. So Trueplay was developed before Sonos had home theatre products, but nonetheless, it applies equally to home theatre products. But it was originally designed for music, and music is created in many different spaces, some of which are shown on this slide. So concert halls, clubs, churches, and perhaps less often outdoors, and of course in recording studios. And increasingly today, music's created in virtual acoustic spaces, that is inside computers. And it may be enjoyed during or after the production process in these same places, but if it's recorded and published, it normally goes through something like this, where a producer or a mix engineer tries to anticipate the end listening environment and prepare the recording for playback, which may be in a place or on a system that looks something like this, but it's more likely to be in places like this. Now, these pictures show some actual end user speaker placements from our user research team internally. And as you can see, the speakers are not always positioned for optimal sound quality. But when the speakers are measured during the prototyping and design stages, a lot of the work is done in a room like this, or rooms like this. More often than not, the room on the right rather than the left. Now, these are interesting places to visit, but you wouldn't want to live in a space like this, or indeed listen to music in there. So we have a delta between the acoustics in spaces where speakers are designed and where they end up being listened to. Now, loudspeaker manufacturers can and do design, tune, and evaluate speakers in a range of real-world settings. But it's fair to say that there's a massive variety of rooms and speaker placements involved in the process of making music and music playback systems. And the last part of the production chain, which is the mastering stage, typically involves tuning the content to optimize the sound quality of the recording across a large variety of rooms through a large variety of music production or sound reproduction systems. However, it's fair to say that mastering engineers today have to make educated guesses about the listening environment, which, as we saw on the previous slide, may not be great. And this slide shows an example of what they're up against. So this shows room average measurements of a single type of speaker. In this case, it's a Sonos Play 1, which is a previous version of the Sonos 1 speaker that we have today. So it's the same type of speaker in 60 different rooms. This isn't speaker-to-speaker variation that we're seeing here. This is variation due to the room acoustics and speaker placement. And as you can see, we've got, you know, in some areas of the spectrum, kind of 25 dB or so of variation, which is huge. So what can be done about this? Well, if we think about what we can do to help the artist's intent come through, we could change the room or the placement of the speakers. Most people probably don't want to move their speakers into a different room just for listening purposes. And some may be up for moving their speakers, but in reality, the placement's probably determined by aesthetic or convenience-based factors rather than sound. And it's probably at least the case, or especially the case for non-audiophile users. Now, another option is to make the speakers in the room sound better by applying corrections to the frequency response. And this is great, and it's been done for decades by professional sound system installers, audio engineers, and audiophiles. However, there are a few notable barriers to doing this for most regular users. First, typical measurements, well, typically multiple measurements will be required, at least if one wants to improve the response over a listening area larger than the size of one's own head. A measurement at one position is most certainly insufficient. It is a three-dimensional problem. Therefore, the user would need to know or be educated about where to take these measurements. Secondly, the methods for measuring acoustic impulse responses or transfer functions typically involve using broadband noise or sine sweeps, and these are not the nicest of sounds to listen to, and they can be aesthetically unpleasant for users. Thirdly, making such measurements typically requires specialist audio equipment, for example, calibrated reference microphones, preamps, ADCs, and software for processing, doing the analysis, making the measurement, and also applying the correction. And this is probably outside the reach of most folk who listen to music. And finally, the measurements can be sensitive to background noise. Less so for broadband noise, but it's particularly so for sine sweeps or chirps. So the environment needs to be relatively quiet for the duration of the measurement. And this is a lot of stuff to consider if you're someone who just wants to plug in a speaker and enjoy the music. Hobbyists might do this at home. Ordinary music lovers will not, and most will not even know where to start. So just to summarize, optimizing the acoustics of the room and the speaker locations within it will improve the sound, but almost always conflicts with other domestic considerations such as aesthetics or simply possible places to put a speaker. And even if it doesn't conflict and the speakers are well placed within the room, getting the best results in most domestic spaces still requires acoustic correction. And the conventional wisdom, which is mostly true, is that acoustic measurements are difficult to perform. They require special equipment and training, and the results are difficult to interpret and apply. So this outlines the motivation behind this work, which is really concerned with the question of how we can devise a method for a regular user, not an audio professional or a hobbyist, to tune their speakers to their listening room. And with that, I'm going to hand over to Dayn, who's going to talk us through the UX and design considerations that were put into developing this feature.
Thanks, Adib. We can go on to the next one. So the key actually to making Trueplay tenable, remember this is 2014, was a close collaboration between user experience, user research, and the engineering team. On the left on this slide, you can kind of see our UX goals. This is how we wanted people to feel. This is how we wanted the calibration process to come across in an emotional way. On the right, we compare that to the requirements for accurate calibration as dictated by the engineering team. So our job was to mesh those two things together and make sure we got a usable calibration from the experience that matches up with the experience benefit. Here you can kind of see some of, we wrote these in ways that were from the customer point of view, right? We wanted it to seem fun and easy and approachable and something I could do. I have time to do it right now. It doesn't seem like it takes an engineering degree in order to be able to do it. And ultimately, in the end, we wanted them to feel smart for having opted in, and getting them to invest a little bit in the customization of the speaker for their space also reflects, we think, in the perception of the improvement in sound quality. So let's dive into each one of those. Our approach on this was to break down the technical requirements into UX chapters and just break them down into steps. And we make each step appropriate and make each step try and feel or achieve those emotional intents we saw on the previous slide, while still meeting the technical requirements. So we'll visit each one of these chapters here. Before we do that, on the next slide, we realized this was going to be a crawl, walk, run kind of approach. Adib mentioned the original intent for Trueplay was automatic Trueplay for the speakers to tune themselves without any sort of user interaction. So they would just always sound as good as they could for the space. We weren't going to be able to do that, obviously, with Trueplay 1.0. So this is manual Trueplay. What you're looking at here is the original sketch from Sonar, as it was called back then, code name, for the crawl approach to this. And these days we do it all the time at Sonos, especially in research and development. But in the early days of Trueplay, rapid prototyping and iteration as a collaborative process between design and engineering was kind of new territory. But the approach that we took was an iterative one, right? So we would build a GUI wizard, a flow of steps, and we would film folks doing those steps. Then we would evaluate the results for technical usability and experience value. And this rapid iteration technique kind of became our go-to tool for developing Trueplay 1.0. And we worked and redesigned that cycle sometimes as many as 3 times in one day. So let's take a look at each one of the steps. And then Adib, keep me honest here about the DSP relevance on each one of these steps, because my lens is decidedly from the design side. Here we go. So the first chapter, low background noise. This is actually pretty straightforward. We use the phone's mic to test the ambient noise in the space. And if it's too high, say from traffic noise, HVAC, or quite honestly, most of the time from children playing in the background or just general family noise, we can't tune, right? The signal noise ratio and all of that. So pretty straightforward here. First chapter, check the background noise. If it's too high, then we can't move forward with the tuning. We'll give you a punch out point for that. Next chapter, spatial coverage of the room. So like calibration processes that preceded Trueplay, we started with recording calibration tones from static locations in the room. And in 2014, kind of the UI flavor of the day was Vine, if any of you remember that, where you would hold down a button to capture a clip of video, and then let up on the button, hold down the button again, you capture another clip of video, and in the end, the process would stitch together a 6-second video of that. So we're trying to draft off of the momentum of that idea, capturing 4 different locations in the room with a hold down kind of UI, figuring that we could use that kind of process or that user behavior that was becoming kind of well known in the interaction space for capturing audio to stitch together to schedule a calibration recording. We tried different approaches to that took the form of a straight dry instruction, which you see here on the left, to a 4-piece band metaphor from above, which you can see on the right, where you would stand in each one of the places you would if you played an instrument in the band. And then the one in the middle is just a treasure hunt style. You walk around the room and we'll tell you when to stop and record a sample. All decent ideas. And we felt pretty sure that we could get the users to perform those actions and walk people through it. But we weren't satisfied with the 2D nature of the static samples. And it didn't feel quite magical experience-wise. It just kind of felt kind of lipstick on what already existed, capturing, 4 static location recordings in the room. And Tim Sheen, who Adib mentioned, the lead audio engineer, introduced us to a new idea to make this feel a little bit more magical and actually improve the technical aspects of it. The technique he introduced us to would become affectionately called the room dance. We still refer to it as such today, but this is a continuous capture technique that asks the measurer to move the microphone around the room while sampling, essentially collecting thousands of samples or of randomized locations in 3D space rather than the 4 static 2D technique, kind of where we started. So we adopted this fluid 3D technique from here forward as what was going to be our new capture process. And this must have promised a big step change in outcome, because undoubtedly this put a higher strain on both the signal processing team and being able to communicate this new technique. This hadn't been done before, as I'm aware of, this calibration capture technique. So folks would have to learn this and perform it nearly perfectly on the first try. So we tried many approaches to try and communicate how to do the room dance technique. And you can see here that went from everything from animated GIFs to videos to illustrations. But in the end, turns out nothing worked as well as a video, an instructional video, showing someone how to do the technique. All right, so this is the final produced instructional video for the sample capture step, or the room dance as we call it. I think it's a testament to how simple it looks once you actually view it, but getting it to be this simple and getting everybody to understand it so simply took a lot of work to get here. I think we did 15 at least iterations of that video right there. All right. So this is the final tuning screen in the app that the user sees while they're capturing audio. There's just enough info here to keep the user on task and give them a sense of the progress without demanding so much attention that they trip over something in the room, because they are walking around and moving the phone up and down at the same time. And then for the design nerds here on the call, the circular progress bar and a central cancel X button in the middle of that little progress bar are a little bit of foreshadowing for the rest of the process. The story of Trueplay kind of sucks the room response into this animated circular element on screen, and then we do the magic, and at the end everything expands back out to full screen into full room glory when Trueplay is complete, which you'll see in a video here at the end. Adib, you want to talk us through the tone?
Sure, yeah. So here's an example of a stimulus tone that's used in production today. So this example shows a tone for a 3-channel soundbar plus a sub. So there's a left, center, right, and sub channels. For a given channel, the stimulus consists of three main parts. There's constant periodic pseudo-random noise in the low end, below approximately 200 hertz. There's a train of chirps from around 200 hertz upwards, and gaps in between the chirps that contain no signal above the noise band being measured. For a multi-channel stimulus tone, as shown here, each channel gets the same stimulus tone, but it's rotated in time based on the number of channels being measured. So the entire stimulus tone is played out of all of the speakers or channels simultaneously. This is typically repeated for more iterations than is shown here, where only 2 repeats are shown. Each channel also contains a unique channel marker to enable identification on the measurement device, channel identification. And this is simply a notch in the high frequency part of the spectrum beyond where we measure or apply changes in the frequency response. So let's have a listen to this tone. And again. Okay, so there are a few important aspects to this stimulus tone that distinguish it from the types of tones that are typically used for measuring speakers in rooms, for example, broadband noise or a full range ascending sweep. So once we've decided to have the user continuously move throughout the space, taking the measurement, as opposed to making multiple static measurements, this immediately constrained the possible stimulus tones that we could use. A lot of in-room speaker measurement methods use broadband noise, and indeed this is what acoustic and audio systems engineers typically use when making in-room measurements of speakers. Now, random broadband noise could be used if the goal is to measure a single channel or an aggregate of multiple channels, but only with a measurement in a static location. Now, periodic pseudo-random noise is an option with a moving microphone, but only in the low end. At higher frequencies, the signal must be short-term, compact in time and frequency to avoid the temporal smearing at higher frequencies that you would get when the user's moving around the room. Therefore, the next option was to use a sine sweep or a chirp. We want to get a good spatial average for all frequencies. Therefore, in order to do this, we shorten the chirps and repeat them as the user moves around the room. Now, the types of sweeps that are typically used for in-room measurements are significantly longer than what we see here. They're normally in the order of tens of seconds, and for a good reason. Which is background noise, right? Because you want to increase the integral of the signal energy over time for each frequency band and maximize or increase your signal to noise ratio. Now, this can generally be mitigated by repeating the chirps enough times and hoping to get enough measurements with a good SNR. And this is exactly what we do with Trueplay. However, with short chirps, even when they're repeated many times, they still have one major drawback for us. A lot of background noise in typical domestic spaces is dominated by low frequency energy. For example, hums and roars, they tend to be quite brown in spectral shape. And with a sine sweep, there's simply not enough time spent in the low frequency part of the spectrum of the sweep to ensure a good signal to noise ratio. So one way to deal with this is to simply turn up the volume of the sweep in the low end and amplitude shape it. However, some of our speakers, for example, the Sonos One, they simply don't produce enough low frequency output to do this without hitting nonlinear processors such as limiters. And also, we would end up subjecting the user to fairly loud test signals in the room, which we want to avoid. Therefore, the solution to having a stimulus that would be robust to background noise in the low end was to have this periodic pseudo-random limited noise, band-limited noise to cover this part of the spectrum. Now, this plays continuously for the whole duration of the sweep, so it gives us a better SNR than we'd be able to achieve with a simple sweep in this end part of the spectrum, but it also gives us a better spatial coverage in the low end as well. Now, finally, for purely aesthetic purposes, we use a downward sweep. Simply, we think it sounds better. However, we do also amplitude shape the chirp to reduce harshness. I don't know if this really comes through in the graphic here, but this is to avoid the kind of whiplash type sound or effect that you get with constant amplitude chirps. Now, this does reduce the signal energy in the high end, but as I mentioned before, background noise tends to be quite brown in shape. Therefore, there's typically less background noise at higher frequencies. And this is a really good example, really, of where we can improve the user experience and the aesthetics of the stimulus tone without compromising on performance by using a little understanding of the acoustic environment and the nature of noise in the space.
Right, that's a good transition to this step, avoiding non-linearity. Adib tells me this is about trying to keep the tone signal clean and free from distortion. I think Adib, you just mentioned we settled on 50% system volume as it being kind of the sweet spot, which seemed just enough for our signal to noise ratio requirements and not to engage the limiters on the speakers themselves, and not too much as to blow out the user's ears for 60 seconds as they're performing the tuning process. Eventually, we did add some intelligence to the ambient noise test that would detect if your phone had a case on it that would obstruct the microphone and that would interfere with tuning. And when we'd ask you to either to take the case off if we felt like it was going to interfere with the tuning. And then the room dance. So I thought we were about to win crazy design awards with this step that you're looking on the screen here. We built a concept that used the phone's camera to guide a person doing the tuning, and they would keep the speaker itself in the crosshairs while we collected the measurements. And by changing the aperture of that circle, we could control the distance and kind of angle from which the person was doing the recording, and therefore, get enough samples from around the room. Unfortunately, the reality of where the mic is placed on the iPhone and people's tendency to keep their hands in contact with the phone in this sideways orientation quickly dashed our dreams. And to date, this is still one of my favorite, only with rapid testing, learning, teaching moments. I think about how far this genius idea, which I thought it was, could have gone before its flaws were discovered if we weren't doing rapid testing. It took us, less than 60 seconds and one participant to find out we actually had a dead concept on our hands here that seemed absolutely brilliant. You can see from the sketches versus reality of a person performing the tuning, her hand there is entirely cupping and blocking the microphone. So in the end, to clear the microphone from obstruction, all we had to do was get them to flip the phone upside down. Super simple Occam's razor solution to this, much more than what I had hoped was going to be the landscape with the targeting element and everything else. Anyway, we made this step 100% achievable with something that I do believe is a kind of a gangster UX move, and that is we flip the entire UI 180 degrees at this step, which basically forces the user to flip their phone upside down and hold the mic unobstructed, pointing upwards. Okay, so on this one, we had to make a decision early on to go iOS only for Trueplay, and it's not only because our user base was heavily skewed towards iOS use, and that was part of it. Part of it is also, even if it's not your primary handheld device, there's a good chance there's an iOS device in the house where you have access to one. But it would have been kind of untenable to address what this slide illustrates as a problem here, is that the mic system or variance within models in Android is much higher than it is within iOS. And from the iOS system, just because of the much smaller number of models to deal with and the smaller amount of variance we measured across models within iPhone, that made the decision kind of for us to go with iOS only for calibration, just for the predictability of the results of the system. Adib, you have a comment about this, right?
Yes, it's the unit to unit, as Dayn said, it's the unit to unit variance which we saw to be considered significantly lower for iOS devices. We do see considerable difference between models. So one thing we do is, whenever a new iOS device gets released, we purchase a bunch of models or obtain a bunch of units of that model and create a calibration file for the mic system. So there is that kind of calibration part of the process that's happening behind the scenes there every time a new model gets released.
Right. Easier to do just within the iOS family, not so easy to do with every model of Android phone that's possibly out on the market, and the new ones that are released all the time, right? Yeah. All right. And then finally, the measurement has to be repeatable and consistent. In fact, resetting, stereo pairing, adding, removing a speaker from home theater are all events that trigger and prompt someone to retune with Trueplay. So it couldn't be a one and done process. We had to make the whole process be able to be, from the user side, entirely repeatable and not feel like a burden. And we fully expect that you'll likely be tuning a player more than once in the manual sense. Adib has a chart here showing actually this is repeatable from the point of view of doing the room dance with the same speaker, different tunings. That's what we're looking at here.
Yeah, it's the same speaker, same room. So, yeah, the speaker placement hasn't changed. So exactly the same acoustic environment, but different room dances. So the user's kind of taken a different, yeah, it's been a different kind of measurement process, if you like, each time, or a different instance of the measurement process each time.
Yeah, and you can see here, remarkably consistent, even though these are entirely different tuning processes. I think that the variance here is a maximum of 3 dB or so. I think you were saying.
Yeah, there's one I think it's, what is it, around 300 hertz. There's about a 3 dB variance there, but for the most part, it's kind of less than a dB of variance for repeated measures, which is pretty good in our view.
Pretty good, yeah. All right, so on this slide, this is the entirety of the Trueplay process as a manual Trueplay process as it exists today. This isn't for home theater. This is for what we call an all-in-one, so the standalone speaker, not a home theater speaker. We'll play the whole video, but Adib, we can fast forward through this.
Sure.
Here's a case removal step that ended up preceding the testing the background noise. This is making sure that you were tuning it in the room where you intended to have it. So you didn't tune in one room and then decide to move it to another room. This is testing background noise. And then the instructional video for how the technique was going to be performed. I think I skipped over the 180-degree flip, but we are, imagine now you're holding your phone upside down. There you go. Now the magic. And there you go. So there's that full screen celebration tone where I was talking about before, where we pull the room response into the phone, we do some magic, and then we explode it out into the rest of the room here. Didn't really come through on the video, but we designed the celebration tone actually to show off the freshly tuned speaker. It's actually for many people the first full range sound they hear coming out of the speaker itself that isn't a button press or something like that. The first thing that you potentially hear from a Sonos speaker is that full range celebration tone. So we worked with the sound designer and mastering engineer to make sure it was showing off the full breadth of a fully tuned Sonos speaker.
So we recently conducted a customer survey that I'm just going to pull a couple of results from here. So the first question is how do users find the tuning experience? So the actual process of performing the Trueplay measurement, or the room dance, as we affectionately call it internally. So the exact question was, please describe your experience in Trueplay tuning your speakers. So this particular survey question had just over 2,000 users respond. It was conducted towards the latter part of last year, and the results are shown here. So I think it's quite remarkable that, or the thing that really stands out is that 96% of users didn't find this process difficult. They found it, easy, somewhat easy, or a small percentage were kind of indifferent to whether they found it different or hard. And I think this really kind of highlights the importance of all of the work and learnings that went into the user research and the design for this process. The next question was looking at the sound experience and how users find the actual result of the process. So the question was, how satisfied or unsatisfied are you with the sound quality of the Sonos products after running a Trueplay tuning? And the results are shown here. Now, we recognize that we're asking people who are most likely non-trained critical or not critical listeners, quite an open and informal question about sound quality. But nonetheless, these results kind of highlight that for the vast majority of users, along with the previous set of responses, not only was the experience easy, but the result was also a positive one in terms of sound experience. With that, we're going to conclude the talk. We will be attending the virtual session with a poster and a chance for Q&A. We'd like to thank you for taking your time to attend this presentation, and we look forward to any discussions and questions that come up in the virtual poster session.